Hey everyone, and welcome. Let's talk about antibiotics. They're probably one of the biggest game changers in modern medicine. Something so common, we barely think about it. But behind that little prescription is a full-blown microscopic war, a battle of wits between our chemical weapons and the bacterial invaders they're meant to destroy. And trust me, the strategy behind that battle is way more fascinating than you might think.
So how does this tiny pill know exactly what to target inside your body? How does it hunt down and wipe out a bacterial infection with billions of cells, all while leaving your own cells totally unharmed? Well, that's the big question we're diving into today.
And this right here, this is the entire mission brief. It's a concept called selective toxicity. The goal isn't just to kill, right? It's to kill with incredible precision. You have to find a vulnerability, a weak spot, in the enemy that we ourselves just don't have.
To pull this off, we've developed a whole arsenal of different weapons, and each one has its own unique plan of attack. This isn't about one magic bullet. It's about having a range of specialized tactics designed to hit bacteria where it really hurts. Okay, so think of this bacterium as a tiny little fortress. As you can see here, antibiotics can attack its outer walls, they can shut down its internal factories, they can disrupt its critical supply lines, or they can scramble its command center, the DNA. Each one of these is a unique weakness, and we're going to break down these tactics one by one.
Let's kick things off with the most famous strategy of all, the one that penicillin made famous. This is the brute force approach, a full frontal assault on the bacterium's main line of defense.
So the target is the cell wall. You can think of it as this rigid, mesh-like armor that gives the bacterium its shape and, more importantly, protects it from bursting. And here's the absolute key. Our cells, human cells, don't have one. It's a perfect bacteria-specific target. So how does this attack actually work? Well, a bacterium is always busy, constantly repairing and expanding its cell wall. Penicillin and its cousins act like saboteurs on a construction site. They sneak in and they block the enzymes that create the final crosslinks. Think of it like taking all the mortar out from between the bricks of a wall. Without a complete reinforced wall, the bacterium just can't handle its own internal pressure. The outer membrane gets weak, water floods in, and the cell, well, it literally explodes. It is an incredibly effective and final way to take out the enemy. This wall-busting strategy is the signature move for some of our most important antibiotics. You've got the beta-lactam family, which includes penicillins, cephalosporins, and carbapenems. Think of them as just different models of the same powerful weapon. And another big one, vancomycin, uses a similar tactic to bring that wall down.
Okay, but what if you can't just breach the wall? Well, the next tactic is to take the fight inside and shut down the bacterium's entire production line by going after its factories.
See, every living cell needs proteins to survive. They're built in these tiny molecular factories called ribosomes. So if you can stop the ribosomes, you can stop the bacterium from building, well, pretty much anything it needs to live.
This slide shows the sabotage perfectly. A ribosome is like an assembly line, right? It reads genetic blueprints to build proteins. As it says here, drugs like tetracyclines jump onto a specific part of this machinery. They physically block the blueprint, the messenger RNA, from being read correctly, and the whole assembly line just grinds to a halt.
And there are a couple of ways to pull this off. Some drugs, like the aminoglycosides and tetracyclines, they target that smaller 30S part of the factory. Others, like macrolides, go after the bigger 50S part. The exact target is a little different, but the result is exactly the same. No proteins, no life. Our third and final major tactic is maybe the most clever. It doesn't just stop production. It goes right for the enemy's command and control center, its genetic code. For a bacterium to multiply, it has to copy its DNA perfectly, over and over again. This whole process needs a bunch of special enzymes and essential building blocks. If you can mess up any part of that supply chain or the copying machine itself, you stop the infection from spreading. Sulfate drugs are basically masters of deception. You see, bacteria need to make their own folic acid. It's a vital ingredient for making new DNA. Sulfonamides look chemically a lot like one of the raw materials they need. So they slide in, jam up the enzyme, and block the real material from getting in. And here's that selective toxicity again. We humans don't make our own folic acid. We get it from our food. So the drug only messes with the bacteria. It's brilliant. Other drugs attack the process even more directly. The quinolones, for example, they take out an enzyme called DNA gyrase. That enzyme's job is to uncoil the DNA so it can be copied. Without it, it's kind of like jamming the zipper on the blueprint itself. Nothing can happen.
Now, wouldn't it be a great story if it ended there? We have these amazing weapons, we use them, the war is won. But bacteria are living things, and for as long as we've been attacking them, they have been evolving ways to fight back.
And one of their best counterweapons is an enzyme with a very specific job. Basically, what this is saying is that some bacteria have figured out how to produce their own defensive enzymes that can literally disarm our antibiotics before they even get a chance to work.
This shows the counterattack perfectly. On the left, you see the core of our weapon, that critical structure called a beta-lactam ring. Now look to the right. Resistant bacteria have developed their own weapon, beta-lactamase. It's an enzyme that acts like a pair of molecular scissors, and it's designed to do one thing: find that ring and break it, making the antibiotic totally useless.
So this brings us to where we are now. The modern age of antibiotics isn't just about finding new ways to attack bacteria, it's also about figuring out how to overcome the enemy's constantly evolving defenses.
The really crucial thing to get from this timeline is that this has always been an arms race. Just look at the gap between discovering a new antibiotic and when bacteria start to resist it. It can be shockingly short. What started with the miracle of penicillin has now escalated to a point where we face multi-drug-resistant superbugs, and that's a serious threat to all of modern medicine.
This invisible battle continues every single day. We understand the tactics: breaching walls, halting factories, scrambling code. But as the enemy adapts and builds new defenses, the question we all have to face is, where is our next breakthrough going to come from? Thanks so much for watching, and be sure to look out for the next video drop.